to solve, particularly for a pipe flow. Now, while solving by numerical methodology, you have to use the computer. That is the computer programming that has already been covered in your computer program. Now, question is, what are the main features of a computer that helps in numerical analysis? Obviously, one of them is the algorithm, as already have you gone through. Hmm. And there are four distinct features while doing numerical analysis that has to be followed when you go for computer to do the numerical analysis. The first feature is number one, is obviously the algorithm in terms of computer program is stored in the computer. Stored in the computer. So what happens, whenever I require, I simply call that algorithm in the form of computer programming, and that can be done repetitively. That is the beauty of the computer, and this execution of the instruction can be repeatedly whenever you want, wherever you want, you can do. So that is the first characteristics. Second is, whatever result obtained from that algorithm and computer programming, that is also stored along with this program, stores the computational value or computed value, or there are values. And you can also retrieve those values whenever you require that. That is the second important. Please write down all these things. Please write down. Number three is the sequence of operations. Sequence of operation, which is obviously very important. The sequence of operation is very important, and that also sometimes, while the results are going on, you have to alter. For example, maybe that while solving, say for the pipe flow, you may come across E equal to 0, V equal to 0, which is not at all a physically possible result. Physically possible result. So what happens? You have to change the sequence, or the maybe even in the algorithm, or the some special technique has to be implemented. So sequence of operations, though it is stored and accordingly computer program is performed, yet depending on the results, or depending on the procedure, you may have to change. That can be also done. Finally, finally, you should remember in a computer program only plus, minus, multiplication and division, and no other is that will require x, log, x. Nothing is possible to do by a computer. So they are basically transferred into this. Maybe p to the power x is broken into series and just computed and added. Similarly, log x or anything, sin x, cos x, etc. So, while doing a numerical analysis, you should always try to transfer the special mathematical operation into plus, minus, multiplication, or division. Now, now, what does it mean in a nutshell? That is, to solve a mathematical problem, say it is a solution of a differential equation by a computer, a step-by-step procedure has to be followed, which has an algorithm stored in the computer, has to be performed, has to store the data if required. That data retrieve is possible and further use is possible. If required, the sequence of operation of the algorithm that has also to be modified or altered, and the elementary mathematical operations that has to be strictly followed, plus, minus, multiplication and division, involving all these and doing a total algorithm, or total procedure is termed as numerical analysis. It's termed as numerical analysis, and this is the this is the task in numerical analysis. Now, so that includes the numerical analysis. And in a numerical analysis, two things are very important: the representation of the numbers and error analysis. Before going in details, we should start or explain what is number one, the floating point representation of numbers, because this is very important and success of a numerical process depends on this. There are two type of arithmetic operations available in a computer. Two type of arithmetic. One is integer arithmetic. Integer arithmetic. Other is real or floating point arithmetic. Arithmetic. Now, what is the feature of integer? Suppose we have 7 plus 8. This is called operation. This operand. This operand. But this can be also like this. That is 1.5 plus 3.97. These are also operand. And this is operation. So this comes under the purview of integer arithmetic, and this comes under the purview of real or floating point arithmetic. So actually this is only for counting. Basically, and this is for subscript. For example, A1, A2, or A1, A2, that cannot be, it cannot be a 1.5, never. Huh? So similarly counting, there cannot be 3 boys, 3.2 boys. So 1, 2, 3, etc. like this. But real algebra is nothing but the floating point arithmetic, which is the very important part of the computer operation. And in a real or floating point arithmetic, the way the numbers, particularly real numbers, are stored or used is called normalized floating point mode. Normalized
স্যার নরমালাইজড ফ্লোটিং পয়েন্টটাকে আরেকবার বলবেন?
বলছি, আমি এক্সপ্লেইন করছি, তারপর তোমাকে আবার বলবো। ফ্লোটিং পয়েন্ট মোড আগে এক্সপ্লেইন করে নি। হ্যাঁ, এই দুটো বুঝেছো তো, ইন্টিজার আর রিয়েল or floating point arithmetic, এটা
হ্যাঁ
বুঝেছো?
হ্যাঁ হ্যাঁ
Actually floating point means real, that is it must have a decimal. It has a characteristics and a mantissa, but in case of integer you don't have any decimal point or any mantissa. For example, to computer 7 to you 7 and 7.0 is same, but the two computer they are not same. Here requires only 1 byte, here requires 3 byte. So economically, operational and all other respect, they are different. They are different, and also their presentation requires lot of caution and lot of technique that I will explain. And usually the majority of the arithmetic operations are real or floating point arithmetic. So that's why the normalized floating point mode or the presentation of the real or floating point operand, that is the data, is very important. Huh? Let me go to another window. Suppose we have a hypothetical computer, and a computer is the hypothetical, and there we can only locate or store 6 digit, suppose 6 digit, 6টা digit, ধরো 1 2 3 4 5 6, এই 6টা digit আমি ম্যাক্সিমাম স্টোর করতে পারবো in its location or what, এটা কম্পিউটার nomenclature, memory location or memory what. I can store only 6 numbers. ঠিক আছে, এবার আমার what I have in my mathematics infinite range of numbers, can be anything. Say for example I have a number 1 2 3 4 5 6 7.8921320012567892115, etc., etc. But the important thing is, whatever may be, I can store in this computer only 6 with along with this their sign. So I have 3 here along with sign. Sign can be also functions. I can store. So I cannot store all this number. I have to make a compromise to store this number. Even I cannot store the characteristics of this number totally, fully. Suppose I have, say, not this number, I have a number which is 4256.42. This is the number, and obviously this is plus sign. So this is one memory location or what. It is the computer nomenclature, and you have to understand this memory location can store only 6 digit along with the plus and decimal sign, and some plus minus and decimal. So here it is plus, that is the sign of the sign of the number. So this is the sign, and how I will do 4, 2, 5, 6, and this is the decimal point. This is assumed decimal point, assumed decimal point, and then 4, 2. So that is the presentation or storing this number to the computer location of this hypothetical computer or the computer we are considering or we are focusing. Now, if we follow that, then what the maximum number I can write here? 9999.9. That is the maximum I can write. I cannot write in this mode. If I go on, this is mode 1. Mode 1. If I go in this mode, maximum I can store this number. Minimum I can store 0.01 minimum. That is the minimum I can store. That is the minimum I can store. But this range is not sufficient for my mathematical operation. So basically, this mode is questionable. This is not very much efficient mode. So how I can use? I can use in a different way. I can use a different way. How? I can use in this way, which is called normalized floating point method, where thus I can use the significant digits. That is the maximum number of significant digits. What are the significant digits? Significant digits are those numbers where the leading zeros are excluded. So in that significant digit, using in a normalized floating point mode, I have two things. One is my mantissa and my exponent. My exponent. So the mantissa is obviously it is less than 1 and it is greater than 0.1. For example, let us and the exponent is basically having a power of 10. For example, let us take 44.85 into 10 to the power 5 or 10 to the power 6. 10 to the power 6. Okay. So how I can represent this? I can represent this for this because it can store only 6 numbers. So I can represent this 1, 2, 3, 1, 2, 3, 4, 5, 6. I can make this point or simply no 0, 4, 4, 8, 5, E8. This is basically 10 to the power 8. So what I can do, I can write here 4, 4, 8 5 8, where plus is my sign, and here plus is sign of exponent, that is e to the power plus 8, and it is sign of the number, sign of the number, sign of the number, and I can store this. So it is a much higher value than 0.999 point 0.01 or 09, much higher than this. হ্যালো, বল, আছি, বল। আপাতত ফাঁকা আছে। বৃহস্পতিবার কটার দিকে বলতো? না, তাহলে আমি ওই 11টার থেকেই আসবো, আমি একটু তাড়াতাড়ি চলে আসবো। ঠিক আছে, ঠিক আছে। আমার যদি তোর গাড়ি থাকে দিতে পারিস, তার কারণ না হলে আমি। আচ্ছা আচ্ছা, ঠিক আছে, ঠিক আছে। যদি যাওয়ারটা ব্যবস্থা যদি যাওয়ারটার ব্যবস্থা দিতে পারিস ভালো হয়, তাহলে আর রিক্সায় যেতে হয় না। হ্যাঁ, ঠিক আছে, ঠিক আছে। হ্যাঁ হ্যাঁ, আচ্ছা আচ্ছা আচ্ছা। So that is the storing way of this number. However, if so maximum
4485 আছে। তো ওইটাতে পয়েন্টটা মানে কিভাবে রিপ্রেজেন্টেড হবে?
এটা ডেসিমাল পয়েন্ট। ঠিক আছে,
মানে স্যার, মানে এই মোডে আর কি সবটা ক্ষেত্রে আমি পয়েন্টটাকে ডেসিমাল ধরবো, এটাই তো?
তাহলে আমি এখানে কি করতে পারি, এখানে আমি বেসিক্যালি এখানে আমি 0.999 into 10 to the power 99 পর্যন্ত সলভ করতে পারি, তাই না? আর মিনিমাম আমি করতে পারি 0.1000 into 10 to the power minus 99. So range has become very large. Come on.
10 to the power 99 কি করে হচ্ছে? 9 হবে না?
না, একটা জিনিস আমি ভুল করেছি, এটা 0, এটা ই নয়। ই ওখানে নেবে না, তো আমি ভুল করেছি। ওটা তো নাম্বার ই কি করে নেবে? Come on, it is the exponent form. মোডটাই এরকম। ওকে,
মানে এইভাবে যদি কোনো নাম্বার এই ফর্ম মানে পয়েন্ট দিয়ে
এটা তাহলে ম্যাক্সিমাম, এটা তাহলে মিনিমাম, তাহলে আমার বিশাল মানে প্রায় তো আমি সবটাই কভার হ্যাভ কভার অলমোস্ট, তাই তো? হ্যালো,
স্যার তাহলে আরেকটা যদি এক্সট্রা ডিজিট থাকে তাহলে কি সেটা রাউন্ড আপ হয়ে যায়?
রাউন্ড অফ করে নিতে হবে, তোমার যদি আরেকটা এক্সট্রা দিয়ে রাউন্ড অফ করে নিতে হবে, সেটা পরে আসে, সেটা রাউন্ড অফ করে নিতে হবে। আপাতত আমি ধরে নিচ্ছি যে এই যে 4 ডিজিটে রয়েছে, মানে তোমার যদি 5 ডিজিট থাকে তুমি রাউন্ড অফ করে নাও, সেটা এরারে যাবে, সেই এরারটাতে আমি আসছি, কেমন? সো this is the normalized floating point mode, and এই normalized floating point mode কম্পিউটারে আমি যদি ডেটা স্টোর করি, if I store the data according to this normalized floating point mode, then I have a wide range, almost numerically আমার যা লাগবে কভার করে আছে, beyond that probably no need practical purpose. ওখানে ই নয়, ওখানে জিরো হবে, সেজন্য তোমাদের একটু বুঝতে অসুবিধা আছে, বুঝতে পেরেছো? বুঝতে পেরেছো? হ্যালো,
ইয়েস স্যার।
হ্যালো, এবার তোমরা তো 11-12 এ ম্যাথমেটিক্সে নাকি ফিজিক্সে বোধ হয়, যারা সিবিএসই, ইউ হ্যাভ স্টাডিড দি সিগনিফিক্যান্ট নাম্বার। হিয়ার লুক, আমার কিন্তু 6টা সিগনিফিক্যান্ট নাম্বার অ্যালাউ করেছে কম্পিউটার। কম্পিউটার has allowed me 6 significant number. 1, 2, 3, 4, 5, 6. Apart from, I can only give 4 significant number. এখানে 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 4টি significant number লিখে I have sacrificed 2, reduced 2, but by that I have gained 10 to the power, a range of 10 to the power 198. Difference between these two. তাহলে I have got a, that is 10 to the minus 99 থেকে 99. I've got this range, which is a huge range. So my normalized floating point mode is very efficient in numerical analysis, and therefore we will always use this mode. Come on. Now we যে সবকে বলে জিজ্ঞেস করলে যে রাউন্ড আপ এবার করতে হবে কিনা,
আমি স্যার ঋষভ।
ঋষভ বাড়ি, তাই তো?
স্যার।
আচ্ছা, দেখো তাহলে if we go for errors কিন্তু আমাকে এস্টিমেট করতে হবে, বিকজ নিউমেরিক্যাল অ্যানালিসিসে error at a particular iteration may be very small. For example, say error is say 10 to the power minus 3. So you are seeing, say absolute, আমি absolute বললাম 0.001. You can say it is a small number, but iteration can be say 50,000. So per iteration যদি এই হয় মাল্টিপ্লাইড, যদি সেটা মাল্টিপ্লাইড হয় which is becoming a very, very big number. Indeed, a big number. Therefore, error should be analyzed, and error should be such that it is not multiplied in the iteration, or rather, with the iteration, it should not grow, it should rather decay. Decay. To do so, we have to analyze the error, and error analysis or accuracy analysis is very important. Now, errors in numbers. What are the errors? Errors in numbers. Whenever I am representing a number or computer is doing some critical operation, what are the errors? Number one error is the finite representation of a irrational number. Finite representation of a say of a number, say 1/3. It is infinite. 0.333. So you cannot represent infinite. You don't round, even if you don't round off, you simply cut. Then finite, you do the finite repeater. So you cannot go up to infinity, up to 10 to the power 90, that is 9, up to 99 you have gone, which means there are some error. So a finite representation is causing error in numerical analysis. Number two is what Rishabh told, is the round off error. That is rounding errors. Actually, what is that? Suppose I have 0.48567 into 10 to the power 8. So here I cannot represent, as I have told you, that hypothetical computer all these matrices. So I have to add here 1. So make it equal to 0.4857 into 10 to the power 8, which means basically I am rounding off. And that is the round of error. And it is very nasty error. It is very nasty error. Estimation is very difficult. Nasty error. It cannot be methodically identified or estimated. You have to go for thumb rule, and that is not a very good one. So round of error is a very nasty error and very fatal error. And finally, number 3 is the truncation error. Truncation error. What is that? Suppose you have an expression e to the power x. So given it's 1 plus x by factorial 1 plus x squared by factorial 2 plus x cubed by factorial 3 plus ... plus x r by factorial r plus ... up to infinity. Up to infinity. Or say 1 minus x to the power minus 1, which is 1 plus x squared plus ... plus x r minus 1 plus ... up to infinity. So in that case, if you have that, you cannot write all the numbers. You have to truncate at some place. So this is basically truncation error. Truncation error. So this type of error It is very fatal if you do not estimate it and utilize this error minimization process, then it will be in numerical process very much fatal. So you have truncation error can be manipulated or you can control that, and that has to be controlled with a very meticulous way. So these are the main. There are other errors also. I will explain. There are other errors also. For example, maybe maybe number 4, the inherent error. Inherent error. Inherent error. Inherent error, what is that? That is the very inherent in nature to the problem you sought or you are focusing. For example, suppose if you solve the Navier-Stokes equation, what is that? I have told you the other day. Del U del T plus plus U del U del X plus V del U del Y equal to minus 1 by rho del P del X plus mu by rho del square U square. Del square stand for del square U del X square plus del square del Y square. Similarly, this is X equation. This is Y equation. Del P plus U del P del X plus V del P del Y equal to minus 1 by rho del P del Y plus mu by rho del square V. Here, this is the this is the local term. Local term. That means in a flow field, say there is a flow field, velocity mu. At any local point, that is basically del U del T means x, y is constant. You have the partial derivative u test. So it is local. That is, I have fixed the space locally. They are my variables, or also called unsteady term, because with respect to at a local point, how it changes. And this is convective. Convective means convection. As if this derivative is on a board U, and on that board du dx is being convected. So this is called convective term. Convective term. And this is the driving unit. In any physical process, there must be a driving unit. For example, if there is a cyclone, the temperature difference is this driving unit. Jeta drive korche. So this is the driving force. Driving force. Driving force. A driving force ekhana aro chilo gx, that is gravity. But gravity negligible. Why? Negligible. And this is called diffusion term.
Sir, এই টার্মস গুলো আরেকবার বুঝিয়ে দেবেন?
নিশ্চয়ই বলবো।
এই যে লোকাল টার্ম, আনস্টেডি টার্ম, কনভেক্টিভ টার্ম।
দেখো, local terms is that is a partial derivative money. Partial derivative means I have del u del t means I have xy constant. আমার del u del x mean I have t constant. একটাকে constant রাখতে হবে। That is the partial derivative. Idea of partial derivative. So at a local place xy, say দুই তিন, how the velocity is changing with time, that I am observing. That's why it is called local term, or also called the unsteady term. আর এই যে ইউ ডেল ইউ ডেল এক্স, ইট ইজ কল্ড কনভেক্টিভ টার্ম। কেন? এটাকে এইভাবে ভাবো যে ইউ হলো একটা নৌকো, ইউ ইজ এ বোট, তার উপরে যেন বসে ডিইউ ডিএক্স ওই মেথডটাতে যেন যাচ্ছে, এই যে ফ্লোটা হচ্ছে সেখান দিয়ে যেন যাচ্ছে। So that's why this a convective term is the most khatarnak things in mechanics, and that is called convective convection হচ্ছে। And this is called diving. একটা physical process তো diving force থাকতে হবে, diving force না থাকলে physical processটা চলবে না। এখানে pressure difference is the diving force, and this is the diving force term. Also gravity ও থাকতে পারে, কি থাকতে পারে, ড্রাইভিং ফোর্স, প্রেসার, একটা পাম্প বা কিছু একটা দিয়ে, বা তোমার একটা গাড়ি চলছে, হ্যাঁ, একটা ড্রাইভিং ফোর্স থাকবে, তো তবেই তো মোশনটা হবে, হ্যাঁ। And this is basically diffusion in any process, any physical process, diffusion হবে, হ্যাঁ, সেটা গ্যাস ফ্লো হোক, এমনি ফ্লো হোক, or একদম সলিড মেকানিক্সে হয়তো এটা জিরো, কিন্তু আদার মেকানিক্সে, plasma mechanics or any other physical flow, concentration change, etc., there can be change in the diffusion terms. So these are, আমি যদি এবার না আমি এটা বলতে যাচ্ছি কেন, say these are my solution domain if I go for fluid mechanics solution. The inherent difficulty is the Navier Stokes equation is such that if you go on finite element analysis, then it fails. A solution diverse করে যাওয়ারই কথা, না আসারই কথা, because it fails some characteristics test. A characteristic test in Navier Stokes fail করে, which means এটা তোমরা ওই থার্ড ইয়ারে যদি ফাইনাইট এলিমেন্ট অ্যানালিসিস করো তখন সেখানে পড়বে। জাস্ট আমি এখন একটু বলার জন্য বলছি। সো হোয়াট হ্যাপেন্স, ইট হ্যাজ দ্য ইনহারেন্ট এরার, অর সে দেয়ার ইজ এ ফিজিক্যাল প্রবলেম, সেই ফিজিক্যাল প্রবলেম সামান্য এদিক ওদিক হলেই দ্যাট সলিউশন ক্যানট বি অবটেন্ড। দোজ আর কল্ড ইনহারেন্ট এরার। ইট ইজ ইনহারেন্ট উইদিন দি definition of the problem or physical process of the problem. For example, আমরা কি করি, PV equal to nRT বলি, কিন্তু এটা কিন্তু নয়, এটা এখানে ইনহারেন্ট প্রবলেম আছে। আমরা কিন্তু প্রেসার A by V square plus V minus V equal to nRT করি, কিন্তু because এটা ভ্যান ডার ওয়ালস ইকুয়েশন আমরা নিই, তার কারণ এর কিছু ইনহারেন্ট প্রবলেম রয়ে গেছে। সো দ্যাট ইজ ইনহারেন্ট এরার অলসো। এবং ইনহারেন্ট এরার কিন্তু মোর অর লেস সব প্রবলেমের মধ্যেই থাকবে, কোনোটাতে কম কোনোটাতে বেশি। সো দ্যাট ইজ দেয়ার ইনহারেন্ট প্রবলেম। And another error which in numerical analysis একটু অন্যভাবে আসে, গ্রিড জেনারেশন যেটা আমি আগের দিন দেখিয়েছি, গ্রিড জেনারেশন। What I have shown this is my domain of solution, pipe. So my domain of solution was actually half. আগের দিন বলেছিলাম তো, মনে করো। So what I am doing, আমি কতগুলো গ্রিড বানিয়ে একে ইনফাইনাইট পয়েন্টস থেকে ফাইনাইট কতগুলো পয়েন্টে আমি ট্রান্সফার করেছি টু রিপ্রেজেন্ট দি ডোমেন। এবার এই যে এখানেই তো আমার হয়ে গেল, এখানে আমার ট্রানকেট করলাম। সো আই হ্যাভ ট্রানকেটেড দ্য ট্রানকেট বলছি, ডিসক্রিটাইজ দ্য ডোমেন, ডিসক্রিটাইজড discretize করেছি, discrete পয়েন্টে ভাগ করে দিয়েছি। I have discretized the domain. তার মানে কি, তার মানে আমি এই জায়গাগুলো নিলাম না, এই জায়গাগুলো নিলাম না, এই জায়গাগুলো নিলাম না, এই জায়গাগুলো নিলাম না, কোনো এরকম জায়গাগুলো নিলাম না। নিয়েছি ডিসক্রিটাইজড পয়েন্ট, তাহলে ওখানের মধ্যে কিন্তু আমার থেকে একটা ইনহারেন্ট এরার অলরেডি ঢুকে বসে আছে। হ্যাঁ, একটা এরার ইনহারেন্টও বলতে পারি, সেটাকে বলা হয় ডিসক্রিটাইজেশনের জন্য। সো দ্যাট ইজ দিস এরার ইজ কল্ড ডিসক্রিটাইজড এরার, ডিসক্রিটাইজেশন, ডিসক্রিটাইজেশন এরার। হ্যাঁ, এটা 6 নম্বর ডিসক্রিটাইজেশন এরার। হ্যাঁ, ঠিক তেমনি আমি তোমাদের আগে দিন এটাও দেখিয়েছি, ডেল ইউ ডেল এক্স কে আমি ডিসক্রিটাইজ করেছি। অ্যাকচুয়ালি ডেল ইউ ডেল এক্স টা কি? লিমিট ডেল্টা এক্স টেন্ডস টু 0
স্যার
ইউ এক্স।
এই ডিসক্রিটাইজেশন এর পার্টটা একবার বলবেন, আমার গ্লিচ হচ্ছিল।
হ্যাঁ ঠিক আছে, আমি বলবো। ডেল্টা এক্স এটা করেছি এখান থেকে, এটাই তো ডিইউ ডিএক্স মানে, তাই তো? ফ্রম দি ফার্স্ট প্রিন্সিপাল অফ দি ডিফারেন্সিয়েশন, মনে পড়ে?
না স্যার ওটা বলছি না, মানে এই গ্রিড জেনারেশনের পর থেকে আমি কিছু করতে পারি।
আমি বলছি, তুমি দাঁড়াও। হ্যাঁ, সো হোয়াট আই হ্যাভ ডান দেয়ার, আমি কিন্তু এই লিমিটটা তুলে দিয়েছি। লিমিটটা তুলে দিলে কিন্তু ওটা মিনিংলেস ডিইউ ডিওয়াই, কিন্তু আমি নিউমেরিক্যাল অ্যানালিসিসে ফাইনাইটে যাব, ইনফাইনাইটে যাব না। এটা করি অ্যাপ্রক্সিমেটলি, কিন্তু আমি কিন্তু ডোমেনটাকে কিন্তু ফাইনাইট করে ধরি। ডেল্টা এক্স টেন্ডস টু 0 নেইনি, ডেল্টা এক্সটাকে আমি ফাইনাইট নিয়ে নিয়েছি। এই ফাইনাইট নেওয়ার জন্য আমি যখন একে যখন ইউ আই প্লাস 1j মাইনাস ইউ আই জে ডিভাইডেড বাই ডেল্টা এক্স করেছি, তখন আমি এটাকে বেসিক্যালি ইকুয়েশন, হ্যাঁ ইকুয়েশন ডিসক্রিটাইজেশন করেছি। এর জন্য তো আমার ওই যে এই ডেল্টা এক্সটেন্স মিলে অ্যাকচুয়ালি হতো, তো সেটা তো ফাইনাইট। আই হ্যাভ টেকেন দ্য ফাইনাইট English. Okay. So I have taken it finite. So there is I have assumed an error. So here also discretization error is there. So discretization error comes both from domain discretization, DOMAIN, domain discretization, as well as PDE, partial differential equation discretization. যেটা বলছিলে বলো, কি জানতে চাইছিলে, তোমার কি অসুবিধা হয়েছে? হ্যালো?
না স্যার, আমার মানে আমি শুনতেই পাইনি বলে জিজ্ঞেস করলাম, এমনি স্যার বাকি বুঝতে পেরেছি।
তাহলে কি আরেকবার রিপিট করতে হবে? রিপিট করবো?
না স্যার, ক্লিয়ার স্যার।
আচ্ছা দেখো, look, what I have done, I have to solve del u del x plus del u del t plus u, whatever may be the equation in all the points, because I have to maintain the continuum. I have to maintain the continuum in physics. But what I am doing, I have limitations. If I want to do all the points, then along this I have to take infinite number of points. Along this I have to do infinite points. Even if I have to do x, y, z, z direction or nite hobe, that is theta direction. Eta holo r theta z, that is cylindrical coordinate, pipe er moddhe jacche. So theta direction o amake I have to take the grid points. Supposing that the boundary conditions and others geometric is symmetric, axisymmetric, so del theta is minus 0, no change along the del direction. So I have to do the discretization along r direction, along z direction. If I do so, if I want to make continuum, so I have to make it. Infinity means very large, say 5,000 point, 5,000 point along this. So here also 5,000 along this. So total number of point is 25 into 10 to the power 6, which means 25 million points. Right? 10 lakh. 10 lakh, এটা basically 10 lakh. So 25 million points. 25 million point में लेकर काम करना ऐसे कोई कंप्यूटर आज तक पैदा नहीं हुआ, बनाया नहीं. So what happens? You cannot do. So what you have to do? At best you can take 500 points. Yeah. At best you can do 500. Yeah. Which means you have to go a difference of delta x or delta y, which means you have to discretize the domain, not all the points, continuity, not all the points there. So what happens here? Already when you discretize the domain, you yourself assume that some error must be there, and that error you are take that is acceptable, and that is called discretization error. Even here also I told you del u del x limit delta x tends to 0, but I am taking delta x to be finite. So here also I am assuming some error which is called discretization error, because this is called discretization of the equation PDE, and this discretization equation also gives some error. So domain discretization, partial differential equation discretization gives some error, that is called discretization error. So these are the it is for 5, not 6. These are the 5 types of main error. One is finite presentation. Actually, number 1 and number 3 are basically same type, but they have some operational differences depending on the presentation of the exponential and other mathematical terms. And they are almost similar type. And the rounding of error, I already told you, that is a nasty error which cannot be estimated, and that has to be your experience, your talent, because you have to go by thumb rule and repeated use of the algorithm. You have to minimize that. And fourth is the inherent error, inherent to the problem, definition of the problem, and fifth is the discretization. So all are these error are there in a numerical procedure. So a numerical procedure. Now, let us estimate the error estimation. Error in numerical process, error has to be estimated. Error estimation. And here it is very confusing and very what I should say, illusion is there. What happens? One error is called absolute error. One is called absolute error. Other is called relative error. Say for example, I first explain this one. Say M1, say fx equal to 0. It's one of the solution is M1. M1 is the right solution theoretically, but numerically I got M2. So my error is M1 minus M2, and I take the absolute, and this I called error in absolute term. Absolute term. For example, say M1 is my value, which is correct, 10 to the power minus 6. M2 is 0.5 into 10 to the power minus 6. So my ERR absolute is basically 0.5 into 10 to the power minus 6. And this is a very large value. It appears that 10 to the power minus 6 is small, but actually it is very large. Why? Why? Say, another case, my M1 is 10 to the power 6 and my M2 is 0.99 into 10 to the power 6. So my difference is basically point, my difference 0.01 to 0.1 into 10 to the power 6. That is the absolute value. Now it appears that it is very big, but if you can go the relative error analysis, you will find that it is not. So what is the relative analysis? Relative analysis, that is number two relative analysis is basically my M1 minus M2 by M1 is my error relative. So first case, ERR relative is 10 to the power minus 6 minus 0.5 into 10 to the power minus 6 divided by 10 to the power minus 6. Absolute is 10.5. 0.5. In the second case, I made it red. Second case, I made it red. It is 10 to the power 6 minus 0.99 into 10 to the power 6 divided by 10 to the power 6, and that is coming to be 0.01. Look, this is much more less than, and this is, though the value is in terms of 10 to the power minus 6, this error is much higher. Much higher. Actually, if we go say my M1, my value is M1 equal to 3. So my M1 is 3.452. And actually, I have to consider the significant number. Significant number is say 158, 1.58, 0.158, 0.00158, all has three significant number. Significant number 3. So actually, what significant number you want, that you should keep in your mind. So say 3.452 is the correct value, but you are getting actually say that is error getting 3.4, you have an error of 0.0005. 05, you are getting this one. Obviously, this is less than equal to M1. Less than equal to M1, and obviously 3.45, actually less than, plus 0.00, 0.05. 0.005. So here my relative error is basically point difference between the error divided by 3.452, which is coming as 0.00029. 0.00029. And supposing that this M1 is now say 1. It is 1. Sorry, 0.1. So it can be, we can get it as it is a 0.9995 for significant point, suppose I want to get. So obviously that is less than 0.1004 significant, and obviously that is less than 1.005. So here also you can see the E is 0.0001 divided by 0.1. 0.1 is the actual, and here you can see it is 0.001. So this means the relative error, whatever number actually that is the correct number is there, the significant digit has to be kept in mind, and accordingly what significant number you are going to keep, or to finally target that will be my convert result. That is very important. And in this way, remember, for this case, remember the floating point error or relative error, say 4 digit is must be error must be 0.0001, or it is 10 to the power minus 4. So if it is the significant number is 4, so it is this. If the significant number is n, so it will be 10 to the power minus 7. So error has to be in that range. So actually you have to be very much critical and very much accurate. What is your significant n? N kitna hoga? For example, if your flow is such that the velocity of the fluid will be 1.05, so maybe you can be critical, say 19. You can be critical. Okay, if I have this, I have this minimum value, it is okay. So you have, look, 1, 2, 3, 4, 5 significant points. Accordingly, you have to be 10 to the power minus 5 accuracy or error condition you have to go. So why I am telling, because in the last day I told you that we have to guess a value, initial guess. Can you remember? Initial guess. That is, I told you that whatever may be my value in this domain, I have to guess at all these points initially u value, guess value. So guess value kya hoga? That has to be very judicious. Judicious. Will come that. Hello everybody.
Yes.
আমাদের একটু তাড়াতাড়ি যেতে হবে। হ্যাঁ বলো, কিছু বলবে?
না।
আচ্ছা, আমাদের একটু তাড়াতাড়ি যেতে হবে। হ্যাঁ, একটু তাড়াতাড়ি না গেলে আমরা এখনো ইন্ট্রোডাকশনেই রয়ে গেছি। হ্যাঁ, ইন্ট্রোডাকশনে রয়ে গেছি। তাড়াতাড়ি কেন যেতে হবে? আমাদের অনেক নিউমেরিক্যাল মেথডোলজি আছে। One of them is the iterative method. সেটা কি? এটার সঙ্গে তোমরা সবাই পরিচিত। All of you is accustomed with this. So it is quadratic. Maybe you have it is cubic. Maybe you have uh, that is quadratic, that is 4 to the power 4. So what happens in all this? There is definitely a definite relationship. For example, in this case, the leading difference is x1 minus b plus b square minus 4ac divided by 2a, and x2 equal to minus b minus over b square minus 4ac by 2a. And it is very, everybody knows. Here also the equation which seldom keep in mind here also. But thing is that doing this in combination to this is very tiresome, and you have to go for lot of calculation, or rather go to the iterative scheme, which is basically trial and error method. And usually we human beings don't like that. Why? Why? Because lot of iteration has to be done. Doing that is very tiresome, takes time, and almost inherent to the error. So we have to use someone that can do very accurately with less time, and that is the computer. So that numerical computations has to be done by a computer. Sequentially, solution has to be done, and the formula has to be find out for that, or the methodology for that has to be sorted out, and then we have to go for the solution. And that obviously, while doing so, that trial and error method, we have to keep in mind what are the errors, how to minimize those errors, and ultimately get a converged solution. My question is how I even though I don't like it, how I take a route, take a iterative process for solving a polynomial, as I have told fx equal to 0. Obviously, the root of this solution of this equation is the solution. Now, now thing is that I have to go for iterative cycle. I have to go for iterative cycles. But I have to gauge the value, initial values. Number two, I have to I have to formulate a methodology to do so, or solution. Number three, uh, to perform it fast. That is, use the computer. Number four, what are the difficulties to do so and time taken. Finally, which is very important, when and how to stop. When and how to stop. Again, So let us take let us take if it's equal to 0 is a polynomial. Now we have to solve it. We have to solve it. So initially we have to guess. The first one is initial guess. Initial guess. শুনতে পাচ্ছ নাকি ইন্টারেস্ট পাচ্ছ না? কোনটা বলো?
হ্যাঁ শুনতে পাচ্ছি।
ইন্টারেস্ট পাচ্ছ না নাকি?
হ্যাঁ পাচ্ছি।
Initial guess. সেখানে what I have told you must be judicious. কি করে বুঝবে judicious? The solution we don't how कैसे समझेगा कि initial guess is judicious? तुम तो जानते ही नहीं क्या solution है. Solution करने के लिए जा रहे हो. You don't know the solution. If you know the solution, then only you can have the judicious choice. हाँ, अगर तुम जानते हो कि मेरा solution एक का नजदीक आ जाएगा, then only you can have the initial guess and take 1.01, 1.2, 1.1, etc. So what to do? Say for example, you have a something, something in the name equals. The best way of guessing is simply mix x and fx. If you put -4, it will come -90.2. If you put -3, it will come -38.4. If you put -1, it will come -9.1. -2. -1, it will come 2.9. 0, 4.0. 1, 0. 2 -3. 3, 1.1. 4, 18.1. Now plot this. Along this x, along this fx 0, 1, 2, 3, 4, -1, -2, -3, -4. -50, -50, And now if you plot it, it will go something like this. Huh. So solution is coming 1.25 or 5. I think 5 it is. 1.5 minus 1, 2.5. Nearly that. But it is a graph. You cannot have exactly. Huh? So you have a rough estimation where it can be 0. Now, for solving in this region, you can take guess value for 1 minus 1.6 or minus 1.55, etc. And that will be a judicious choice. For solving 1.01, 1.2, 1.25, etc. will be judicious. So, for judicious choice, what you have to do, if you have to actually initial guess, and that guess has to be very much judicious. Now, what other thing you can do?
স্যার স্যার একে তো 0 এসে যাচ্ছে, তো একের চারিদিকে আবার গেস মারবো কেন?
একে 0 আসেনি রে বোকা, ওইটা তো আমি একটা প্লট করলাম, প্লট করে দেখছি একের মধ্যে দিয়ে যেতে পারে। ওটা 1.005 তো হতে পারে।
আচ্ছা,
হ্যাঁ, এটা তো আমি জাস্ট প্লট করলাম, অনেকগুলো ডিসক্রিট পয়েন্ট নিয়ে মোটামুটি একটা এভারেজ কার্ভ টানলাম। ঠিক আছে?
হ্যাঁ
হ্যাঁ, না এটা তো একটা, দিস ইজ গেস ভ্যালু, এন্ড গেস ভ্যালু করে তারপরে আমি ইটারেটিভ মেথডে যাব। one of the method of the iterative method is the successive bisection method. Or method of successive bisection. সেটা কি? ধরো তুমি মোটামুটি suppose you say तुमको मालूम हुआ है in a certain range this is the curve, जैसे मैंने बताया तुम कर्व ऐसे बना के देखा है, but exactly not this point, it is approximate. Curve plotting is there only. Now you know this point from the curve approximately, उसके पहले वाला एक पॉइंट लो, say that is x0, इसके आगे भी एक पॉइंट लो, say that is x1. So if x0 is negative and if x1 is positive, which means there is a solution in between these 2 points. In between these 2 points. So we have to exactly take where it is exactly by derivative method cutting the x-axis. To do so, what we will be doing? We'll take a point x2, which is the bisection of x1 minus x0. That is x1 plus x0 by 2. So basically we take x2 which will be say coming here. So जो इनिशियल में जब हमारा जो ये था इंटरवल था, where we have seen that if x0 is negative, if x1 is positive, that was my initial interval. Right. That was my initial interval. Now my interval has come to this one. So say that initial is now interval has come s by 2. Yes. Now once again I see fx2 and it is greater than 0. From the curve, say I am getting greater than 0. So now I will come x1 को इधर represent करेंगे. So it is now my x1. I am coming closer. Now I once again find x2, which is x0 plus new x1 divided by 2. And suppose this time x2 come as here. x2 come as here. So this is negative. My fx2 is negative. So I can say that around the new x1 and x2 and new x1, my solution lies. Now once again, I will go for this x0 and x1 and find where it is. And I will come close. When I will find that difference between previous x2 and present x2 is almost previous x2 and present almost coming a very small value, and it is also the fx2 is coming almost 0, then that is my solution, and this is called the bisection method. Have you understood?
Yes, sir.
Yes, sir.
Okay. So that is not a very difficult one, very difficult one, and it is the method of bisection. Another one for today. Another one for today is Newton-Raphson iterative method. Second. Iterative method for solving polynomial. For solving, and once again, same. If you go for it can be theoretically also analyzed. I will explain first by the geometrical method, then go for theoretical analysis. It is fx, it is x. Suppose this is. So I take a point. I take a point here. X0. And I make a tangent here. It is starting here. This is the angle theta. This is the angle theta. And this is my x, mu x1. So I come here. I see this is positive. And fx1 is very large. So I once again draw the tangent. And I come x2. And this is my fx. Once again I come here and I get x3. And this is my fx. And in this way, finally x1, x2, x3, x4, when the fx is becoming less than any pre-assigned value epsilon, then that xn, xn, x equal to xn is my solution. This is called Newton fraction method. Actually, if you go for theoretical analysis, for the first value, fx0, fx0 divided by x0 minus x1 equal to tan theta, or x1 equal to x0 minus x0 minus x0 minus f0 divided by, this is basically f dash x0, f dash x0. Hello, ঠিক আছে?
Yes, sir.
Yes, sir.
So my algorithm or my general term is xi plus 1 equal to xi minus f xi by f dash xi. Xi. Only thing I have to ensure so that f dash xi never becomes equal to 0. Never becomes equal to 0. Then in this way I will go on carrying finding xi plus 1 when f xi plus 1 almost equal to f xi almost equal to pre-assigned value, then it is the xi plus 1 or xi, whatever may be, is my solution. But here there is a very important thing. Here, if somehow the initial guess is idhar udhar ho jayega, then you will be ending up in an endless cycle, or the root will never become. How? Let me explain that. Suppose the car, instead of that easy, is something coming as this one. So suppose I have taken a point here, which is my x0. Now my tangent is coming here. So this is my x1. Now here my tangent is coming almost here. So I am basically in a do loop, infinite do loop here. I don't have any solution. So, but the solution is actually very near to here. I have to guess, but I have taken a guess here. So I am ending up with an endless loop or endless cycle. Another thing, suppose I have taken here the value. So this is the tangent. So here it is. So this is the tangent. And it will be giving simply x equal to a trivial solution. Here it will go to the x0. Maybe x0 is a solution. So it will go to x0. But if I want to solution at very near, so I have to take a very near to that. That is my guess value should be this one. And that judicious guess value has to be very clear. For example, if my guess value is here, then the tangent is going here in this way. Then what I will do? It will go here. Then the tangent will go here. It is diverging. Here, once again diverging. So in this way, Newton-Raphson method is very much sensitive to the initial guess. Initial guess. ঠিক আছে?
হ্যাঁ,
তাহলে আজকে এটুকু থাক, হ্যাঁ?
ওকে
স্যার স্যার ওই 10 টু দি পাওয়ার মাইনাস n যেটা অনেকক্ষণ আগে বলেছিলেন ওই সিগনিফিকেন্ট ওই ব্যাপারটা না ঠিক আছে
আমি বলেছি 4 ডিজিট সিগনিফিক্যান্ট ডিজিট যদি বলি তাহলে দেখো ওইখানে আমার এরারের মিনিমাইজেশন 10 টু দি পাওয়ার মাইনাস 4 পর্যন্ত করতে পারি 0.0001 দেখো ওখানে তাই করেছি তার মানে সিগনিফিক্যান্ট ডিজিট যেটা আমি ম্যাক্সিমাম মানে অ্যাকুরেসি পেতে পারি মাইনাস অফ দ্যাট সিগনিফিক্যান্ট ডিজিট যদি সিগনিফিক্যান্ট ডিজিট 2 হয় তাহলে আমার ম্যাক্সিমাম অ্যাকুরেসি মানে মিনিমাম এরার 10 টু দি পাওয়ার মাইনাস 2 এবার যদি 3 সিগনিফিক্যান্ট ডিজিট তাহলে মিনিমাম এরার 10 টু দি পাওয়ার মাইনাস 3 যদি n টা সিগনিফিক্যান্ট ডিজিট তাহলে আমার মিনিমাম এরার 10 টু দি পাওয়ার মাইনাস 10 ঠিক আছে ওটা যেটা করেছি সেটা একটু লিখে নিয়েছি তো সেটা একটু নিজে একটু দেখে ইয়ে করো আচ্ছা আজ কত তারিখ জানো
ওকে
14
আচ্ছা দাঁড়াও তোমার যেটা আমি তোমাদের একটা রোল কলের জন্য ইয়ে করেছি না
ঠিক আছে
মানে রোল কল আগের দিন করেছি না
হ্যাঁ মনে হয় হ্যাঁ স্যার করেছি
হ্যাঁ স্যার করেছেন
হ্যাঁ 7 তারিখে ক্লাস হয়েছে আচ্ছা 14 তারিখ তাই তো
Yes.
বরুণ হাসদা,
হ্যাঁ স্যার প্রেজেন্ট। মাইক নেই, মাইক থাকতো।
আজাহার ইমাম, absent. বিদেশ মন্ডল,
Present, sir.
মোহাম্মদ আমির,
Present, sir.
সৌম্যদীপ মন্ডল,
Present, sir.
অনিশ কারার, সৌগত দাশগুপ্ত, দেবজিৎ দাস,
Present, sir.
ঋষভ বারিক,
Present, sir.
প্রিয়াংশু মন্ডল,
Sir.
প্রণয় সুদ,
Present, sir.
ওই বললাম আর কি আজকে আমরা প্রথমত হলো we have tried how to do numerical analysis by using a computer. What are the different steps to be followed? Step by step methodology have to be followed while doing numerical analysis. As I told you earlier that to solve a physical problem, you have to discretize the domain as well as you have to discretize the governing equation. So, by doing so, with the geometry, boundary condition, mathematical formulation, methodology, computer programming, everything, it is in a package is called the numerical analysis. And that numerical analysis, while doing so, by the computer, we have represent the numbers. And that is the normalized floating point mode of representing the number. When we represent that, then we get a wide range of presenting the number into the computer, maybe in the range of 198 e to the power 10 to the power 198. That is the range. So it is a huge range, and therefore almost covers all the numbers which are practically we are handling. Now question is, when we do represent a number, then there are a few errors. Also there are a few procedural errors. First of all, representing a number into a finite form 1 by 3 I have given, maybe 1 by 9, maybe 1 by 7, etc., maybe 1 by 11, etc. So those number is being represented by a finite number which has not at all a finite or they are irrational. So what happens at that case? Some error is slipping into numerical analysis. Number two, round of error. Round of error, as I told you, that is a very nasty error that cannot be estimated a priori, and you have to go for thumb rule or trial and error or whatever may be. That depends on your talent, your experience, and your practice. The third one is nothing but the truncation error. As I told you, e to the power x or log x or 1 plus x to the power minus 1. Those are infinite series. The infinite series cannot be handled by the computer because n cannot be infinity. We have to be very much realistic, and that has to be finite. So whenever there is a finite series, means I am truncating the rest of the part, and that is called truncation error. Now there are some other errors also. One is called the inherent error. What is inherent error? Inherent error is something which is associated with the problem or physics of the problem, and it is inbuilt within the problem. And last one is the discretization. Whenever you go for numerical analysis, either the domain or the solid boundary, whatever it may be, that has to be discretized into grid points to represent the continuum of the body or of the domain. However, if we want to take too much points, then the number of points will be such that present day, still today, whatever the convention, whatever the computer invented may not handle that, and therefore is not feasible. So we have to take number of fixed points. Beyond that we cannot go, and that will not definitely represent the continuum or the domain total. So what happens there? Gives some error, and that error is called domain discretization error. Also, the governing equation has to be discretized. Following lot of rules are there. Maybe I will tell you that. That is forward difference method, backward difference method, center difference method, upwinding method. Lot of difference methods are there. Whatever may we do, actually PDE is being transferred into finite difference method, where we at the very beginning discard the limit delta x tends to 0, which means we are going for a finite difference method, not taking very small, which is going to be 0. So there also gives the error, that is while discretizing the equations. Those are the errors. And the error analysis the next thing for the error analysis, how much error is making estimation and then we have gone two methods. One is the bisection method, one is the Newton-Raphson method. Now before bisection method, I told you that for any numerical method, you has to take the guess value, that is, which is called initial guess, and initial guess is not very easy. So what you can do, your talent, your experience, your practice, all these you will give also the problem you are studying or the problem you are going to solve. There you have to have a very close look, very close understanding what the variables may be. Then you can find only or guess only the values. Otherwise, mathematically or theoretically, what you can do, you can plot the graph that you have done in function in your higher secondary, drawing the graph. Draw the graph where approximately it intersects or cut the x-axis, that is the approximately the value of the solution. So if you guess about that or around that value, then that can be a very good or judicious choice. Otherwise, if you have a wild guess, then if the problem is well organized, well defined, and the governing equation is well organized, well defined, as well as boundary condition, then maybe number of iteration taken is very large, but eventually you will come to the solution because it will converge. But there are some problems which are prone to diverge and which are not well defined from the point of view of physically as well as mathematically, or even any one of that. Then those problems solving by numerical method, if the initial case is non-judicious, you may land at a solution which is not at all near to the or not at all the converse solution, or it will diverge, or you will be in a cyclic way. Now, whenever you draw a curve, you can go for finding the solution by bisection method. That bisection method graphically shows, as I have already shown you. There is a algorithm also. I will show you next step, and by that you can find the solution. Another thing is the Newton-Raphson method, which is a very strong method, and there you have also geometrical I have shown, and by that method is very quicker and very effective. However, remember in the Newton-Raphson method, there if you don't have a judicious choice of initial guess, then you will land obviously to a cyclic endless cycle, or maybe you can have f dash x to be equal to almost 0, then the algorithm won't be working. So this is the in a nutshell all the things I have covered today. And thank you. Good day. Okay.
স্যার স্যার সৌগত দাসগুপ্তা ঢুকেছে।
হ্যাঁ,
সৌগত দাসগুপ্তা ঢুকেছে।
সৌরভ দাশগুপ্ত ঢুকেছে। সৌরভ দাশগুপ্ত
স্যার নেটওয়ার্ক প্রবলেমের জন্য বেরিয়ে গেছিল।
আচ্ছা ঠিক আছে, তোমার মুখটা একটু দেখি।
ও ফেস অন করবো?
হ্যাঁ, ক্যামেরা অন করো।
দাঁড়াও স্যার এক সেকেন্ড।
তোমার বাড়ি কোথায়? তোমার আচ্ছা ঠিক আছে, তুমি কিন্তু প্রথম দিন ক্লাসে আসোনি, রেগুলার ক্লাসে আসতে হবে।
স্যার আগের ক্লাসে এসেছিলাম তো।
না তো, আগের ক্লাসে তুমি অ্যাবসেন্ট।
না স্যার প্রেজেন্ট ছিলাম।